Now we're going to introduce electromagnetic radiation, and then we'll move on to atomic structure. So radiant energy or electromagnetic radiation has wave-like properties and moves through space at 3.00 times 10 to the 8th meters per second. And this is the speed of light in a vacuum. Two of the wave properties are shown here, wavelength and amplitude. We'll look at the third in the next slide. So wavelength is the distance between identical points on successive waves, and it is represented by the Greek letter lambda, which is this right here. The longer the wavelength, the lower the energy, and the shorter the wavelength, the higher the energy. Units of length are used to describe wavelengths and typically are given in nanometers. So wavelength is measured from crest to crest, or it could be trough to trough in that wave. The second property of waves is the amplitude of that wave, and it is the vertical distance between the midline of the wave to the peak or the trough. Excuse me. The third property of a wave is its frequency. And frequency, designated or abbreviated with the Greek letter nu, looks like a little b, is the number of wavelengths that pass through a particular point in 1 second. And the units to describe the frequency are hertz, Hz, or 1 cycle per second, which can also be written as s to the minus 1. And the speed of the wave, given by u, is frequency times wavelength. And these units associated with speed are in meters per second. So Maxwell proposed that visible light consists of electromagnetic waves. Electromagnetic radiation is radiant energy that consists of two components, which we see in this figure, both an oscillating electrical field and an oscillating magnetic field. And these two fields are perpendicular to each other and travel through space together. And electromagnetic radiation is the emission and transmission in the form of these electromagnetic waves. So Maxwell's model proposed that a particular form of electromagnetic radiation has a characteristic wavelength and frequency. And the product of wavelength and frequency equals the speed of light in a vacuum, represented by c, and that speed is 3.00 times 10 to the 8 meters per second. This is a universal constant, so you will get to know that number, or you should actually memorize that number. So all electromagnetic radiation satisfies this equation. Okay. Now we're going to take a look at the electromagnetic spectrum. There we go. In which ranges from type of radiation where we have gamma rays. These are the highest energy or the highest form of electromagnetic radiation. Radio waves are the lowest in energy. And you can look or compare their frequencies and wavelengths. So if we have gamma rays being the highest energy type of electromagnetic radiation, it is going to have the shortest wavelength versus radio waves having the longest wavelength. And if we have high energy with short wavelengths, we have to have a high frequency because that product has to equal 3.00 times 10 to the 8th. And so we see these low energy radio waves have long wavelengths and low frequencies. Of course, the visible light spectrum is in this region, and we've got a blow-up insert of that, and we see that it ranges from 400 nanometers in length to 700 nanometers in length. Now, there were three perplexing phenomena where the experimental basis for the development of what we're going to call quantum mechanics or quantum chemistry. And the first of those was something called black body radiation. And this was solved by Max Planck in 1900. So Maxwell's wave model could not account for all the emission spectra of hot objects. So we will see what a spectrum looks like momentarily, but what it reflects is the amount of energy that is absorbed and released. Black body radiation is a theoretical, or a black body, I should say, is a theoretical object that absorbs all light that falls on it. No electromagnetic radiation passes through it and none is reflected. In other words, it's not absorbed and released. Because no light is reflected or transmitted, the object appears black when it's cold. However, if we transfer light energy into heat, when they are heated, these black bodies, they emit radiation of the same frequency that is absorbed. Carbon, in its graphite form, absorbs about 3% of electromagnetic radiation and is considered a perfect emitter of radiation. So Planck proposed molecules of a body cannot have arbitrary energies, but instead are quantized, or discrete units he called quantum, or packets of energy, and proposed a model that gave wave-like and particle-like properties to light radiant energy. And we also see he came up with an equation that allows us to calculate the energy of what we're going to call a photon, which was originally called a quantum or a packet of energy. We now call that a photon. So this E represents E of a photon, or a packet of light or electromagnetic radiation. There's a constant involved in this equation. It's Planck's constant, represented by that lowercase h, and its value is 6.626 times 10 to the negative 34 joules times seconds. We're going to do a couple problems using this equation, keeping in mind that H equals 6.626 times 10 to the negative 34 joules times seconds. And we're going to play around with this equation before we do the first problem, but E of a photon equals Planck's constant times frequency. But we also know that C, or the speed of light in a vacuum, equals lambda times frequency. And C, of course, is 3.00 times 10 to the 8th meters per second. So we can derive another equation that allows us to calculate E of a photon by substituting a different relationship for frequency that comes from the this equation. So if we isolate or rearrange to solve for frequency using the speed of light or the product of lambda times frequency, we get C over lambda. So another form or another equation that can be utilized to calculate E of a photon is Planck's constant times the speed of light divided by lambda. Okay. If we substitute our units here, these are typically, or the speed of light is meters per second. Lambda is usually given in nanometers. So we will have to convert nanometers to meters in order to get our units to cancel and end up with just joules. Seconds and meters cancel, and the final unit then would be joules. Okay. In the original equation, this is joules times second, Planck's constant, times 1 over S. So seconds cancel and energy then is in joules. So our energy unit is joules. So first example of the use of these equations, we are asked to calculate. So what is the energy of a quantum of red light? So this means photon. That has a wavelength, or lambda, of 656 nanometers. So because we're given lambda and not frequency, we need to use E equals Planck's constant times the speed of light over lambda. But we need to convert those nanometers to meters. So I'm going to do that down here. So we have, we have a wavelength of 656 nanometers, and the relationship between nanometers and meters is, for in 1 meter, we have 10 to the 9th nanometers. So our lambda in meters equals 6.56 times 10 to the negative 7 meters. So now I can substitute or set up this equation. 6.626 times 10 to the negative 34 joules times seconds times the speed of light in meters per second divided by 6.56 times 10 to the negative 7 meters. Meters cancel, seconds cancel, and E of that photon or quantum of red light is 3.03 times 10 to the negative 19 joules. One more. And there are 3 parts to this problem. I'm going to try to get them all on the side because that's all I allowed for. And we have a strong yellow line. That occurs in the spectrum of sodium. And that is at 589 nanometers. The first question we're asked is, what is the energy of one of those photons in joules? So we're given a wavelength. Okay? So, once again, we have to use the approach that we used in the previous problem. And to start, we need to convert those nanometers to meters. So we have 5.89 times 10 to the negative 7 meters. So E of this photon, we multiply Planck's constant times the speed of light. Whoops. Should have started lower there. Meters per second. And divided by the wavelength. In meters. So E, not sure what happened there, of this photon equals 3.37 times 10 to the negative 19 joules. Okay. Second question, what is the frequency of this wavelength, or nu? So what is the frequency of this wavelength, or lambda? We know, of course, that C equals lambda times frequency, so we can use this equation to solve for frequency, or we can rearrange this equation and solve for frequency. Either works. I'm only going to do it one way, and I'm going to use this equation. So rearranging that equation to solve for frequency, frequency is equal to speed of light divided by lambda. So 3.00 times 10 to the 8 meters per second divided by lambda in meters, 5.89 times 10 to the negative 7 meters. Meters cancel. Remember, frequency is in units of 1 over s or hertz. I prefer to use 1 over s or s to the minus 1 so I can keep track of my units canceling. And this frequency then is 5.09 times 10 to the 14 s to the minus 1 or hertz. And the third part of this problem asks, what is E of 1 mole of these photons? Okay, for that we need to use Avogadro's number. We have calculated the E of 1 photon. So E of 1 photon is 3.37 times 10 to the negative 19 joules. And we need to convert those photons to a mole of photons. And in 1 mole of photons, we have Avogadro's number of photons. So we've canceled or eliminated the photons, and now we'll have units of joules per mole. And this is 2.03 times 10 to the 5th joules per mole of photons. Okay, the second phenomenon that couldn't be explained by Bohr's model of the atom was something called the photoelectric effect, and this was resolved by Einstein in 1905. And it was observed that light shining on certain metallic surfaces caused the surface to emit electrons or photoelectrons. And we see this apparatus here in which we have a metal inside this area or sealed container. And it is also attached to a voltage source, and we have a meter to measure that voltage. And we see light that is shining on this metal, okay? And it was observed that current only flows if the frequency of the light is above some minimum threshold. So a source of radiation with a frequency less than, regardless of its intensity, but less than the threshold value, produces no photoelectrons. On the other hand, even if a dim source of radiation with a frequency greater than or equal to the threshold frequency, that does produce photoelectrons. So if the surface of the metal is irradiated with light of a frequency above the threshold, electrons are dislodged, and any excess energy is imparted to the electron as kinetic energy. Okay? So, light, as we have seen, has both wave nature or wave characteristics and particle characteristics. And the photon is a particle of light. Now we just saw how we can calculate the energy of a photon, and the energy of a photon is given by Planck's constant time frequency, but that also equals the sum of the kinetic energy of that photon plus the binding energy. And the binding energy is the minimum energy required to eject an electron. We won't be using this equation. We can also rearrange this to solve for kinetic energy if we wanted to. You will not be asked to calculate the kinetic energy of a photon, however. And lastly, the third phenomenon that was unexplained by Bohr's classical model of electron structure, or the electronic structure of an atom, was the atomic or the line spectra. Okay? And this A spectrum is the dispersion of electromagnetic radiation into its component wavelengths. So atomic spectra, so these are the spectrum of elements, have a pattern of characteristic wavelengths associated with the excitation of the atom. And we are shown here the line spectrum of hydrogen. So in this diagram or figure, we have a voltage system connected to hydrogen gas that's in the discharge tube, and there's a plate with a slit in it through which the electromagnetic radiation is funneled. And when it hits this prism, then it's separated into its component wavelengths, and we get 4 distinct lines in this hydrogen spectrum. We get a violet, bluish green, and a red, spanning that visible light spectrum. Okay. So a continuous spectrum is given by sunlight and white light, and it contains all the wavelengths in the visible spectrum. A line spectrum, which is what we're looking at here, is a discrete spectrum. It contains light only for specific wavelengths, and the series of these lines is called, for the elements, is called the element's atomic spectrum or emission spectrum. And so what's the significance of this? It shows us that when an excited atom loses energy, only specific amounts of energy can be lost. Thus, we can conclude that electrons in an atom are restricted to specific energy levels, and that the energy of an electron is quantized. And this last figure, or last slide in the intro to electromagnetic radiation, shows a number of line spectra for different elements. If we were meeting face-to-face, I would have brought a demo with gas tubes so you could actually visualize these yourself. But in conjunction with other experimental data or characteristics, we can actually identify elements based on their spectra, or part of the identification process. Oh, and I meant to mention, what is an example of a continuous spectrum or spectra? Think about that. There's one that nature provides us when, oftentimes, it rains. So think about that.